Now for question 30 is an interesting one. Okay. Now the graph, he has an IV graph of a certain component. After that, he asks for the resistance of the component. We have voltage V1. Before we do it, let's run through the basic of resistance. Now, resistance in some of the questions or like maybe where it involve curves or even other straight lines, some of us we tend to have this understanding, okay, that somehow R is actually related to the gradient, okay, of the IV graph. Okay, it's not wrong, but it's not actually correct also. Okay, so in this case, we are not looking at the change in I or change in V, okay, which will lead rise to maybe R is change in V over change in I. Some students even go to the extreme that we're saying that R is actually, well, delta I and delta V is like differentiation like that. Now, I will not say this is correct in the sense that if we go back to the fundamental of resistance, resistance is actually defined as the ratio of the voltage to the current flowing through it. So it's the ratio of V and I. Okay, the keyword here we're focusing on the word ratio. So in the sense that it's not about it's not about gradient. It's just that maybe sometimes the graph that is given to us, okay, the way we find, okay, it happened to be, let's say, IV graph. Maybe it's Omi conductor. It somehow find that the V and the I, we use the V, we use the I, it somehow seems quite similar to like we actually finding a gradient. Okay, but in fact, it's actually not. It's actually the ratio of the I and V. What's the difference? Okay, what's the difference? It literally means that the ratio of the value of I and V. Okay, and the ratio is in the sense that the ratio is actually with respect to I would say the axis to the zero. So here I'll run through the proper method of finding the ratio using an IV graph, and I hope it clear up the matters with you so that you don't actually judge did it wrongly. Okay, now if you look at other questions whereby maybe you look at if you look at like maybe a diode graph, get IV graph. Okay, sometimes like judging by the diode graph, you find that my graph looks this way. If I happen to use the gradient, it really explains the resistance, the change in resistance. Okay, but it's just by coincidence only. Okay, if not, it's actually using the correct method should be you analyze it through the ratio of the V and I. Okay, and you to get, and after that you actually get the resistance of that particular at particular instance, and actually then you can conclude what happened to the conductor itself. But how do we look at the ratio of the V and I of the particular instances? Okay, here I will show you a technique that I said I always use and it always work one. Now, when we look at, let's say for example, okay, this particular for example, this particular point. Okay, if I want to look at the resistance of this particular point, I am actually not looking for the gradient. I'm not looking for the gradient of this particular VI graph. I'm not. The gradient of this particular VI graph doesn't tell me the resistance. In fact, actually what I should do is actually I should draw a straight line. Okay, I should draw a straight line to the axis, okay, to get the necessary V and I. Okay, so example, how do I find at this point T? Okay, at this point number 1. Okay, point 1. How do I find the resistance of point 1? So which means if I want to find the resistance of point 1, I should actually voltage of it at 1. Okay, and the current at 1. So how do I find the current at 1? Okay, the easiest one is actually connect it to the origin. Okay, so if I connect it to the origin, okay, so this I connect it to the origin. Okay, so this is the correct origin. Okay, so if I want to find the value of V and I at position 1, I am actually looking at this particular value. This is my V at 1. And after that, I'm looking at the current at the space here. I'm looking at, sorry, my mistake. So I'm looking at the I of at 1, and I'm looking at the V at 1. Okay, so which means these two lines will actually give me the I and V of this particular point, the resistance of this particular point. Okay, so similarly, what happens to the other point? Okay, so let's say I want to find the resistance of at point 2 here in this case. Okay, if you look at gradient, you'll find, this point 1 and point 2, they happen to be the same gradient. Then what happened? The resistance of this line will actually, the resistance between these 2 point 1 and point 2, it happens to be on the same straight line, so the gradient happens to be the same, and point 2 and point 1 will have the same resistance. But this analysis is wrong one, because gradient has nothing to do with gradient. Okay, it has everything to do with the ratio of the V and I. So how do I get the ratio of the voltage V and voltage I at 2? Okay, same thing, I use the same technique. I get a ruler, so I'll draw a line cutting from the origin, okay, to the point 2. Okay, so this is the point I'm looking at. So this is the line I'm drawing. So the ratio of this, the line, the vertical axis and horizontal, vertical line and horizontal line of this line, this purple line, will give me I current at 2 and the voltage at 2. So in other words, okay, so this will actually be this value here will be actually my current at 2. This value here will actually be my voltage at 2. Okay, so in other words, this is what I'm looking at. Okay, so this is my I2, this is my V2. Okay, sorry, this is my I2, this is my V2. Okay, so in other words, the gradient of actually is not the gradient of this physical line, this IV graph. It's actually the gradient of this line that gives you the resistance of that particular point, at that particular instances. Okay, so in this case, you'll find that, okay, in this case, the ratio, the gradient of this line is actually the gradient of this line. If you take, okay, so it will be I2 and V2, which implies is a resistance 1 over R. Okay, so you'll find that as if you compare these two lines, okay, let's draw this line. Okay, so if you compare these two lines, okay, so let's say you compare point 1 and point 2. Okay, so let's look at this second line. Now, you'll find that by looking at the line, okay, you'll find that line gradient of line 1, the purple line. Okay, the gradient of line 1. Okay, let's erase this. Okay, the gradient of line 1. Okay, the gradient of line 1 is actually steeper than line 2, which means the gradient at line 1 is actually bigger than the gradient at line 2. Okay. Now, and based on this question, you know that the gradient in this case it refers to I1, V1. It refers to I2, V2. So in this case, it means that the resistance of 1 at point 1 is actually resistance is actually V over I. So in this case, the steeper the gradient, okay, the inverse of this gradient will actually be resistance, because the resistance is V over I. So now I have I over V. So it's the reverse. So which means that the resistance of 1 is actually smaller than the resistance of 2. Okay, so you'll find that for this particular analysis, you'll find that if you use the ratio, you'll find that resistance at point 1 and point 2, they are actually different number. Okay, unlike some of us who like to use this gradient to analyze the resistance, you'll find that R1 and R2 happen to be on the same straight line, happens to be a constant straight line, and the gradient actually is the same, which means the resistance will actually be the same. Okay, which is wrong, which is the wrong analysis. Okay, so with this, I hope actually students, you actually pay a bit more attention to the way you analyze the IV graph. And after that, all this, you will find that actually the resistance of V1 based on the question is actually the answer D. Okay, so with this, I hope, okay, it makes sense, okay, or it makes some sense to the word ratio. Okay, ratio is not gradient. Okay, sometimes it looks very similar, but the deep down, the fundamental of ratio is actually not gradient. Okay, so take a look at this analysis. If you have any problems, you can just leave a comment at the video, or you can drop me an email so that we can actually discuss it out. Okay.